Okay, what I want to do in this video, and probably there will be quite a bit of space here in this video where you might get bored. So because we're gonna run an ICA algorithm, which can be kind of a lengthy process. Maybe I'll stop and then restart after we get the results. This is a this is a MATLAB toolbox called EEG Lab. And among other things, it allows us to do independent component analysis. So I'm going to load an existing data set. This is basically something I just pulled out for the class. Hopefully I can find it here without too much trouble. Basically what we're going to do is we're going to load a data set that was just, I believe it's going to be probably 10 seconds of EEG data. So, and this is resting state data. So we can look at the channel data. And so I believe these have been filtered, and with a low pass filter at 0.5 hertz and a high pass filter at 50 hertz. And you can see that buried within this data set are clearly some areas where we have some probably eye blinks. Here's something that's showing up on all the channels. Here's something that's probably the same thing. So actually these data are pretty clean, but you can still see there are some isolated areas where we have some stuff showing up. So within this toolbox, let me pull the window back up. Within this toolbox, we have the tool of run ICA. So let's run ICA. And we're just going to let the default conditions apply. So let me sort of show you what's going on here. Okay, and you can see we're going through a number of steps. This is actually going pretty fast because this data set's not huge. So basically, as it's running ICA, you might remember we looked on the PowerPoint lecture at the different slides where we're looking at what's happening as we're looking for non-Gaussianity among our channels. That we're going through certain steps. I believe there we went through 5 steps. Here we went through 320 steps. Now, what these guys do that the basic ICA doesn't do is after the ICA algorithm has been done, they actually go in and they've created in their software sorting of components. So they sort components in descending order of the mean projected variance. They scale those based on RMS, and then they recompute the matrix. So what this means is this algorithm, originally I said there's not a lot of interpretation of amplitude, nor is there interpretation of ordering. These guys within this algorithm that processes EEG data, because they know something about the basic EEG data set, they have gone in and done some of that for you. So what we want to look at is component activations. Okay, because these basically are the components where they have looked at the independent component analysis components. Now let me see if I can reduce the number of channels that we're going to display to maybe 25 so that you can see more easily what we're looking at. And let's go up to the very top. And let me make some changes on the magnitude of this plot. That's the wrong way. Okay, so here's where things get really interesting. Let me reduce this display even further. Let's go down to 10. And let me go back up again to the top. Okay, you can clearly see right here, this top channel contains some kind of artifact. And now if we look at our time scale, this is showing up slightly more often than once a second. This is a heartbeat. So you're clearly looking at a heartbeat artifact in this first channel. These data actually have already been cleaned using ICA, so we're not seeing a lot of eye movements. Here's an example of one eye movement buried within channel 11. But most of the eye movement data, I believe, have already been removed from this data set from a previous independent component analysis that was done. I could be wrong. Maybe this person in these 10 seconds didn't blink. I know one thing we did when we selected these particular sections of data is we very specifically looked for 10 seconds that were relatively artifact free. So we kind of did some manual pre-processing there. In some of these channels toward the top, you can see the amplitudes are bigger. You can see just the characteristic of the signal looks a little bit different. This one has got something that seems to be a little bit correlated with this heartbeat, so you can see they don't look completely independent. But you see what the components look like. So these are not in any representative order of channels 1 through 60. So now what you can do is you can actually come into this algorithm and you can tell it to reject components. So I can say reject components, remove components, and I can tell it to remove component 1, and let's just remove just one component. Okay, let's accept that. And then it's going to give me a default file name. Tell it OK. So now let's plot the channel data on this new data set. Now what has happened on the new data set is that heartbeat artifact has been removed because I effectively zeroed out the component of the weighting matrix that was responsible for that heartbeat. So let me come back and see if I still have, yes, I should still have the original plot. Somewhere. Let me see. Let's go to the other one. Yeah, here we go. I believe that this one on the left is the one without the heartbeat artifact removed, and the one on the right is the one that has had the artifact removed. So you can actually, I think if you look up here at this top channel, you can see a little bit of the appearance here, here, here of that heartbeat. It does tend to show up across all channels. A lot of that is gone when you look at this version after we have removed that one component that seems to be strongly correlated to heartbeat. So you can do this for heartbeat components. You can do it for if there's noise in a particular channel, one of the components will show up to be much more noisy. I didn't really see that in our component representation. Sometimes you have to go down to some of these lower ones. Number 10 here appears to be more of an artifact than actual EEG. This one looks like something odd. Doesn't really look like EEG. So you look at the time domain signature. Here you see this little plateau looking thing. That's a horizontal eye movement. Channel 27 might be one we might want to consider throwing away if it's truly only representing not channel but component 27. So that's one way to make the decision. Now, this is not related to independent component analysis. This is another algorithm, but this also allows you to look at component maps. So what this component map is going to do is it's going to tell you, based on where your channels are, it's going to give you sort of like a topographical mapping of where the energy of each component is. So as I plot this, if you look at component number 4, you see how that's highly centered around the right eye. Number 3 looks like it's centered right at the front of the face. 3 and 4 probably represent some kind of eye movement artifact based on. So what it does is, okay, it takes your component and it says, okay, what percentage of that component is present in each of your 64 channels? And then it does a topographical mapping of the power there. So notice how on channel 1 we're just kind of diffusely spread out here. It appears that more is being picked up on the right side than on the left side. This is that one that corresponded to the heartbeat. And so possibly, you're picking up some kind of pulse activity on the right side compared to the left. But you notice there's no concentration of energy. Same with channel 19. You notice how diffuse everything looks. It's very spread out. On the other hand, if you look at channel 37 and channel 36, you see how there appears to be power located strongly in an area within the brain. Channel 39, this looks more like a movement, because see how it's kind of located out of the brain, although that might also be a hearing kind of thing or a temporal lobe kind of thing. Look here at 61, how all the energy appears to be outside of the back of the head. This is more likely some kind of noise, just some kind of generic noise. On the other hand, 49, 50, 51, you see how that activity is localized to a brain region. So what we do after we run independent component analysis is we look at the time domain distribution. If it doesn't look like EEG, that's a heads up. Then we come and we look at the power distribution across channels. And if we see something odd, like this channel 3, then we go back and look at the time distribution again. And so we make a decision using these two pieces of information on which artifacts we think we need to remove from the data set. So this is just an application of independent component analysis that runs within a toolbox that has been